Guan is most famous for his channel modeling work for high-speed railways. So let's leave the time for Professor Guan. Yeah, welcome.
Yeah. Thank you, Professor Zhang's very nice introduction. So it's my great pleasure to have the chance to report some progress. So I would like to thank the kind invitation from Professor Wang, Professor Huang, and also other organizers. So this time I would like to present some of our results of under joint undertaking of Beijing Jiaotong University, ZT Corporation, and 3 operators in China. All right, so first is motivation. What is a smart wireless environment? So in the future that we think a smart wireless system should be able to understand the environment, right? And also the environment should receive the order from the communication system. What kind of change I should have in order to optimize the performance of the communication system? So in order to achieve this, the communication system should have very accurate perception and prediction of the wireless environment, which is a fundamental of any high-quality wireless information services. So in order to achieve this goal, we will require digital twin of wireless environments which can enable autonomous network optimization. So mainly speaking, you can have this wave propagation space, and also you have the physical space, but we need a mapping between these 2 spaces so that our communication system will understand the environment and the environment will understand our communication system. So there are some scientific challenges. First, how is the EM field excited? In order to get this, we have to build a library of physical EM property of the materials. And then the question is, how does the EM wave propagate? For instance, when you have a wave in heating on a rough surface, you actually do not only have a reflection, but you also have a directive scattering, unified scattering, and even backward scattering. So actually, finally, you get this green shape, which is quite irregular, very far away from our theoretical assumption. And this radiation profile actually changes along the frequency and the material. So that it's kind of a lot of work. And also when you have higher frequency bands, then you actually have molecular absorption and very large bandwidth, you have the frequency dispersion. So more and more propagation mechanisms are coupled. Finally, you need to figure out how to characterize such multipath channel. For instance, this is a channel transfer function of the amplitude, phase, delay, space, polarization, frequency dispersion of every multipath. So that such kind of multiple dimensional features of the channel should be characterized and represented in a very concise and scientific way. Okay, and this is about the accuracy. And let's see the bottleneck of the digital twin of wireless environments. What is a bottleneck? So let's see the requirement of the digital twin is that the digital twin in the cyberspace should work in the same pace of the real system. So what is the timeline of the real communication system? This is 5G. So you have this 30 kilohertz as a sub bandwidth, and you have 100 megahertz as a total bandwidth, and you have 273 resource blocks. And then that means that every 500 microsecond, every 500 microsecond, you should generate a channel transfer function with 3,276 frequency points. If you can generate channel transfer function or channel impulse response in such kind of high efficiency, then you can say, okay, now I'm not doing simulation, I'm doing digital twinning, right? So the efficiency is actually the bottleneck. So let's see some key technologies that we can do towards the digital twin of the wireless environment. So first is about the physical EM property of the material. So as Professor Zhou also mentioned, so this is kind of our old school work, so that you traditionally bring some material samples into your laboratory and you make the scanning measurement to understand how the wave will be responded in terms of different incidence angle, scattering angle, and then you regress the EM property and then key parameters of propagation mechanism models based on such kind of VM-based scanning measurements. But of course, if in the future more advances that we can use some UAV And then we can get some scanning for the real environment and estimate the multiple material at the same time. I think this is how the similar idea that Professor Zhou also presented. So that would be the future. And then let's talk about the 3D environment model. So thanks to the development of the ecosystem of digital twin, nowadays it's not, so, 20 years ago when we talk about ray tracing, mainly speaking, no users could use ray tracing because there was no digital map or very expensive digital map. But nowadays, actually, very easy you can get this point cloud, raster data, satellite image, oblique photography, table beam, and CAD, and so on. So there's so many diverse formats of the digital map, but the thing that they cannot work directly for ray tracing, right? So what you need is a multi-source fusion for environment model reconstruction. And then, according to such kind of material of diverse formats of the digital map, then you can get some 3D environment model that can be used for ray tracing simulation. And better, this method should be autonomous. But nowadays, of course, we are doing this manually with our students or teachers. But in the future, of course, I think such kind of autonomous fusion mechanism will be developed. And then the last key technology, which is also the core content today, is ray tracing. So here, this is animation to let everybody get the impression of what ray tracing is. So mainly speaking, you get the amplitude, phase, and the delay of every ray in terms of different propagation mechanisms like the transmission, reflection, scattering, and then you got the channel impulse response. So this is what you can see. So this is actually very good spatial consistency. So this today we heard a lot of presentations saying that for the 6G, for the digital twin, spatial consistency is so important, and for ray tracing, this is naturally there. And also nowadays you can also change different viewpoints so that you understand what kind of base stations and the signals from those, how they propagate to the receiver on top of the high-speed train. All right, so all of this work we have been included in the online high-performance ray tracing platform named CloudRT. So that was released in the year 2018, and now we have already accumulated users from more than 100 countries. So recently we just made some statistics. We found that, okay, so a lot of universities like Cambridge University, TU Munich, TU Braunschweig, and NYU, and also ETRI, Samsung, Tokyo Institute of Technology, and so on. So a lot of universities are using, but more exciting that we also found that a lot of industry partners are also using this platform. For instance, Intel, Thales, Viavi, Samsung, Sony, China Mobile, ZTE, Huawei, Vivo, and so on. So, me speaking, we are quite a pleasure to know that a lot of people are really using it. Yeah, but the thing is that we also understand there's a huge limitation of this platform. So, mainly speaking, first, it's offline. So the result is somehow stored in the server. So it's impossible to do anything about digital twin. Another thing is that actually it's purely CPU based. So that sometimes when you use that, especially in the long queue, you think the efficiency is really low. Please forgive us because there's no GPU and so on. So in order to break through these bottlenecks of the current system, we developed a new system named hyper ray tracing. So mainly speaking, we understand actually the different tasks within the ray tracing core actually are not supposed to be only executed by CPU or GPU. These should be assigned to different computing nodes. For instance, this EM computing is very complex. So this work should be finished by CPU. But for a lot of time-consuming work like AI acceleration or geometry tracing of the rays, actually they are just a repeated work. So GPU is perfect to do this work. So that, maybe speaking, the idea is just put the correct task to the correct computing unit, and then you got high efficiency. And apart from this, we also made some other optimization. For instance, for the algorithm, we found that actually, for instance, this is actually the radiation pattern of a traffic sign. You know, traffic sign is a disc and a pillow. And then you find that actually, so this is a radar cross-section, and actually only very limited points are important for the radiation. So which means that there's no need for you to really have a very detailed 3D model for the traffic sign. You just need to put some very significant scattering point in your retracing environment, and then you connect this scattering point with the TX and RX, then you got the relation. Yeah, so this actually can reduce complexity very much. And of course, you should deploy your retracing core on the high-performance computing platform. And also, we did some optimization in terms of the data level. So for instance, here, you can see in the past, what we did retracing that for the reflection point, and then we generate the scattering for all the tiles of the plate. But finally, we found that actually only very limited scattering points surrounding the reflection points actually make sense or make significant contribution. So that you just you can just ignore the scattering from the tiles which are far away from the reflection points. Another thing is that, as also Professor Wang and other professor speakers today mentioned that about the diffuse, it's a DMC, so it's dense diffuse components. So for instance, of course, there's no need to use retracing to simulate each dense diffused components. You can use retracing just to simulate some spectacular reflection, maybe higher order of the reflections, and then you can use, for instance, propagation graph, such kind of statistical method to compensate such kind of diffuse scattering, and then you can get more realistic results. All right, so let's see. We also did some comparison between the performance between the Hyper-RT and Cloud RT. So first, verification was made for the outdoor macro cell scenario. So this is 1 square kilometer, including almost 30 triangles. And then for one snapshot, we totally got more than 500 arrays. And we also simulate, so the frequency is 2.6 gigahertz. And by using this CPU and GPU, actually, which is just a very affordable GPU, not the brand new one, right? And then we got the snapshots of of the CR or channel transfer function at 3,000 to 176 frequency points within 30 milliseconds. So I would say we have more than the improvement of the efficiency more than 600 times. And another thing is that when we go to the indoor factory scenario, which actually is more complicated, but actually for the more complicated scenario, the Hyper-RT's improvement of the efficiency is more clear. So you can see, finally, we also got the improvement ratio around 7,000 times. So finally, one snapshot with more than 3,000 frequency points, it takes you only 30 milliseconds. And also we verify this in a VQ2X scenario. And then we can see that the improvement ratio R finally reached 50. So finally, the average time of Hyper-RT for one snapshot is around 20 to 30 milliseconds, which is of course still quite slow compared to the requirement of the digital twin, which is 500 microseconds. Now it's still like 30 milliseconds, right? But it's still, I would say, compared to the traditional retracing, the improvement is already quite clear. So we have the conclusion that this makes it very promising to realize digital twin in the future with affordable computing resources. So now I will show you a demo that when you have this hyper retracing, what you can do is human-in-the-loop network optimization. So here you can see, so this is average coverage, area coverage, and then if you're an optimizer, and then just change the azimuth angle of the transmitter, and immediately you can get the result. Actually, for every angle, you just relaunch retracing. So very important is that you should have a very fast retracing. Otherwise, then it wouldn't really work. All right. So yeah, of course, when you have a very fast retracing, you can build very high quality data set to train any artificial intelligence network you want. So for instance, we use the data set built by retracing, and then we train a super resolution model. The good thing is that in the future, so this is like the heat map, then you can use very limited points for retracing, and then you use deep learning to compensate the other place, okay? And that is for the normal channel characters. And also we did this super resolution for the cluster level. So mainly you can see this is a full retracing. That is the predicted, so just like 1 point for retracing and then another 7 points for deep learning, and then retracing again. But they are quite similar to each other, which means that we do not need to use retracing for every snapshot. We just need to do retracing once and then use artificial intelligence to guess. And also you can jump into the re level. And then, for instance, because for every re, it's kind of a graph, right? So you can use the result of the retracing in order to train a graph neural network, and then you can directly use artificial intelligence to generate some multiple scattering re's without doing retracing in the future. Yeah, and also hyper retracing can, for instance, generate the multipasses from the objects, and then use that multipasses. You can calculate the redox cross-section, and also you can use it to generate the target movements, and also you can use hyper retracing to generate a micro Doppler effect, and so on. Yeah, so finally, you see this is a millimeter wave radar profile, so measurement and simulation of the hyper retracing. Of course, it's not difficult to make retracing very accurate, but the thing is that how can you make it accurate while very fast? And in our retrace, in the past it's just 1 minute for one frame, but nowadays it's 30 milliseconds for one frame. All right, so my time's up, and I just have one conclusion that. In the future, like 5 years, I think we can have the hope to have a powerful retracing that can really digitoting all the wireless environment in the physical world to the cyberspace. And thanks to all the global partners who have been supporting us for this research for many years. Thank you very much for all. Thank you.
Thank you, Professor Guan. I think you managed your time very well. One quick question, if any. Yeah. If no, then we can discuss offline. Yeah, thank you, Professor Guan. Yeah.